Hi, this will be the last lecture in the series of module 2 and 3, where we were looking at introducing concepts in from linear algebra, which we will use later in the course. So, we were dealing with matrix properties, and one of the important ones which we would have learned some tricks of how to do this is the diagonalization of matrix, or what is, let us first begin by what is a diagonal matrix, right. By definition it's quite clear, and we will deal to begin with, we will actually deal with square matrices. So, a square matrix with non-zero, with non-diagonal entries being 0. So, what are the diagonal entries? So, if I look at say a 3 cross 3 matrix, so maybe this would be the diagonal elements, and all the out diagonal elements would be 0. That's what the is the mathematical expression for this. So, there are only elements in the diagonal, and the out diagonals are all 0. So, it's not necessary that all these diagonal elements be non-zero. For example, you could also have a case like this, that this is also a diagonal matrix, right. Okay. So, and then the next statement, which is also kind of substantiates that the diagonal elements can also be 0. They need not always be non-zero. So, what is the rank? Then the rank of the diagonal matrix is equal to its non-zero diagonal entries. So, for example, here you have 3 non-zero diagonal entries, so the rank here would be 3, and here you have 2 non-zero diagonal entries, and the rank would be 2. Okay. Importantly, okay, so this is very easy to verify that if one asks what are the eigenvalues of a diagonal matrix, well, the entries of the diagonals are themselves the eigenvalues. I don't need to prove this. It's half a line proof, and you could do that by yourself. And another interesting property, if I take a diagonal matrix A and another diagonal matrix B, then the product is also a diagonal matrix, and okay, the entries would just be that. So, this entry is multiplied by this entry, this by this, this by this, and so on. In addition, they are also commutative. Commutative essentially means that if I take A and multiply by B, that is necessarily equal to if I flip the order, right, I multiply B by A, and this is not always true, right. You can just this is a trivial exercise to verify that A times B for a matrix is not necessarily equal to B times A. Okay. So, if I take a matrix A, well, A square will also be diagonal, A cube will also be diagonal, and so on. This is in some sense a product of or consequence of the property which we had earlier. Another interesting property is how does the inverse look like? Well, the inverse of a diagonal matrix is also a diagonal matrix. What are the entries? Well, the entries are just the reciprocal of the diagonal entries. So, for example, here the inverse in the first case would just be 1 0 0 0 1 by 2 and 0 0 0 and 1 by 3. Okay. In the second case, there will be no inverse because it's of rank 2, and the determinant will go to 0. So, this matrix will actually not have an inverse. So, whenever there is an inverse, so the inverse would just be you just take the reciprocal of this diagonal elements. Okay. Now, given a matrix, well, it's not always in the diagonal form. Then I ask myself a question: can I actually bring it into a diagonal form? Why I need to do this? Well, it's to exploit some of the properties discussed in this slide. We will substantiate that a little later, but let us for a moment ask ourselves a question: given a matrix A, can I diagonalize it? Or in other words, can I find a diagonal matrix D which is similar to its original matrix A, right? So, when can I do this? Well, if a square matrix A is similar to a diagonal matrix D, then it is said to be diagonalizable. So, we had something on the similarity transformations the other day, right. So, where we started with say I take two subspaces and I have say some transformation A from a subspace say U to another subspace U. Then here I had another say transformation again from U to U with say some number D here, or the metric representation let that be called as D. And if this side has a coordinate representation of say x a with its basis, and here this has a coordinate representation with x b, and if this transformation from a coordinate representation corresponding to x a to coordinate representation x b is given by the matrix P, this is given by P inverse. And this essentially was the similarity transformation, that D is equal to P A P inverse, right. Okay. So that's what it means, right. So a square matrix A is similar to a diagonal matrix D, right. If this happens, then it is said to be diagonalizable, and let us see what it means in our context, right. So alternatively, as explained here, for a linear transformation F going from say V to V, or here I just use U to U, it's the same thing. So there exists, so this statement means that there exists a basis for V which results in a diagonal matrix corresponding to F. What is the basis here? That is the basis corresponding to this vectors representation X A. Okay. Now, okay, how do we, so given a matrix A, then how do we go to its diagonal form B? So I start with A, and can I realize D? Okay. So what do I know about A? Well, let us say that A has distinct eigenvalues lambda 1 till lambda n and some corresponding eigenvectors E1 till En, right. I assume that say that these are the n eigenvalues and these are the n eigenvectors, and possibly that A is full rank also. So now what I can do here is to find, so the idea is to find, so if this D can be represented as, okay, just to be consistent with the notation, let me call this as E and this as E inverse, right. So D, can I find, or okay, let me call this an E inverse, just again to be a little more consistent. E inverse A E, it does not matter, right, because they are all so it is always invertible. So I can always write one as I can, if I can go from here to here, I can always go from this point to this point. Okay. So can I find, given a, can I find a D such that D, the elements of it are just the eigenvalues in the diagonal entries and remaining all going to 0. Now the question boils down, okay, does there exist a E? If there exists a E, what are those E's that will take me from A to its diagonal representation? Okay. Okay. So it turns out, I'll not do the proof of it, I'll just give you a little idea of what is actually happening here, right. It turns out that this E, or the eigenvectors E1 till En, they form a basis for Rn, right. So these eigenvectors which actually form a basis for Rn are actually is actually the E which will take me from A to D. Okay. So what does that mean, right? So let me just write down in simple terms in coordinates of what does it mean here. So what I had earlier was, I said A times E is E times D. Okay. I know what is, so A is given to me, I want D to be such that all its diagonal elements are the distinct eigenvalues or well, they need not be distinct all the time. They are the n eigenvalues. And what is the E? Then I claim that E is the set of eigenvectors E1 to En, which also form a basis for Rn. So if I just look at say in the two dimensional case, right? Say if I have say A is in R 2 cross 2, right. So what is so can I actually substantiate this statement? This is not a proof, but this is a little illustration of how we can go about doing that. So my A, so what do I know of the relation? So I know that A times A times E1 is lambda 1 times E1, and similarly A times E2 is lambda 2 E2, that given a matrix A. So I have an eigenvector E1 which satisfies this relation corresponding to a eigenvalue lambda 1, and similarly with lambda 2. Okay. So assume I can write A as its independent or its individual entries A11, A12, A21, A22. So I just expand this, right, and I can write this as, so E1 will have its components E11, E12. So this constitutes my E1. Similarly with E2. So this is my E2. This on the right hand side I can write this as again E11, E12, E21, E22 with lambda 1, 0, 0, lambda 2. So well, it's a simple exercise to check this lambda 1, 0, 0, lambda 2. I just take the inverse, go here. This is always invertible because I assume that E1 till En they actually form a basis for Rn. So I have so let me call this now E. So this is E inverse multiplied by A times E will give me this matrix, which is essentially the diagonal realization of a matrix A. Right. So it's a straightforward computation process. Right. So there is nothing really that special that is happening. So when can I do this? Well, n cross n square matrix is diagonalizable if and only if it has n linearly independent eigenvectors. Right. So the reason for that is the invertibility of this matrix A. So if they are not linearly independent, then you may not be able to do this. Okay, what to do when they are not linearly independent is something which we will address later in this lecture. Okay, so there are some simple examples. So I have a matrix given by 2, 0, 6 and minus 1 with eigenvalues lambda 1 and 2, and then these are the corresponding eigenvectors. This is a simple way to do this, and I can easily find as that. Okay, so my matrix E here would be minus 2, 1, 1, 0, and I can compute E inverse A comma E to be, okay, I'll just skip the computations. You will just can quickly verify that this gives me this number 0 and 2. Okay, so this is a very trivial exercise. You can just, as an exercise, compute the diagonalization or the D matrix corresponding to the A matrix, which is given by this set of numbers. Okay, what else can I actually do with this diagonal matrices? That I have a beautiful looking diagonal representation. So one possible application could be, okay, given a matrix A, let's say, okay, well, how do I compute A square? Okay, again it satisfies the condition that it could actually be diagonalizable, that it has n independent eigenvectors. So let's say I can say that A, so what was the expression? We had D equal to E inverse A times E. So I can equivalently write this as A equal to, so this will be E D E inverse. Okay. So what is A square? A square would be E d E inverse multiplied by E d E inverse. Okay, so this is E d square E. Similarly, I can write A cube to be E. So this should be an inverse somewhere here. Right? So okay, it's here. E d cube E inverse, and similarly any kth power can be computed this way. Okay, now this is an easy matrix multiplication, right? So what do I know is, given a diagonal matrix D with entries lambda 1 till lambda n with all the off diagonal being 0, d power k would simply be the eigenvalues to raised to the power k, lambda n power k, and all the others being 0. And I just have to have this two additional matrix multiplications of multiplying to the left by E and to the right by E inverse. Okay, so one may ask a question of, why do I need to do this when actually I can put this into a computer and compute? Well, the answer is it's not that simple, right? So why do I need to learn these techniques? So much of the problems which we deal here would have lots of computational issues, and the idea would be to use as less computational power as possible. So if I just do a matrix multiplication, just take an arbitrary matrix, say it is of large dimension, and I just do a standard, I just write a standard code for matrix multiplication, like the rows and the columns and so on, it will for sure take a larger computing time than just doing this, because here I think so if you just look, the computations here are pretty straightforward, right? As long as I know what the eigenvalues are, and I just have to do two basic matrix multiplications, right? So once I know the eigenvalues, this is tricky to compute, this is very easy to compute. It will just have n computations, and then I just have two matrix multiplications, as opposed to having k matrix multiplications. So what we are doing is not a trivial exercise, but if I were to write this up as code it up, I would possibly use this technique than using this one, and just to save my computing power. Okay, so well, what else can I do? So if I come back to the Markov matrix example which we had in the previous lecture, 0.3, 0.7, and then we were interested in what to compute the value of a power 100, right? So okay, let's revisit this and see if we can verify the results that we had earlier. Okay, so these had eigenvectors of the form 0.6, 0.4, 1 minus 1, and if I so this will have 1 was so eigenvalues were 1 and 1 by 2. So here I will have this E inverse AK, so whatever is here, this will be 0, this will be 0 and power k, and similarly with the inverse element here, this will be my my A matrix raised to the power k, right? So this is just rewriting this here, E, this is E, this is d power k, and this is E inverse, whatever that could be. So what happens as k goes to infinity? Well, as k goes to infinity, I'll have 0.6, 0.4, 1, minus 1, the eigenvectors. This will go to 0. This is anyway 0, this is anyway 0, this is a 1, and corresponding number here. So I can just compute this to be 0.6, 0.4, 0.6, 0.4. Just a little illustration of the kind of computation we did last time to find of how the eigenvector definition actually helped us computing higher powers of A without actually having to do the matrix multiplication 100 times. Right. So this is also one of the easier techniques that one could adopt. Okay. So all this required. So this statement was crucial, right? That it actually needs n independent eigenvectors. Okay. What if that does not happen? Okay. So if it does not happen, it means that I have okay. So, what it means mathematically is that if I have matrices with eigenvalues whose algebraic multiplicity exceeds the geometric multiplicity, then they are defective. A trivial example, just to say, if I take the 3 cross 3 identity matrix 0 1 0 0 0 1. Okay. Here I can always find 3 distinct eigenvectors, say which could be whatever, right, any so any vector in R3 is an eigenvector, and I can always find 3 distinct eigenvectors, and in that case I can, so all these 3 eigenvectors E1, E2, E3 will span the entire of R3. It may be possible in examples such as this that that there could be, so the eigenvalues here are 3 and 3, and the algebraic multiplicity is 2, and you can actually check that the geometric multiplicity is 1, that you can only find one independent eigenvector given these eigenvalues for this matrix A. Okay. So, it could be, okay, you could also have examples where these eigenvalues are distinct, right, and then so if you have an example like 1 0 0 0 2 0 0 0 3. So, here so the algebraic multiplicity is always equal to the geometric multiplicity, everything is 1 here. Okay. So it could also happen where, so here you have multiple eigenvalues. So, algebraic multiplicity is 3, geometric multiplicity is 3. Here for each eigenvalue it is 1 comma 1, 1 is the algebraic multiplicity, 1 is the geometric multiplicity, and so on for each of these eigenvalues 1, 2 and 3. This is a little trivial example, but good in understanding. Okay. So, defective matrices, so all these matrices which we considered in this previous sections were such a way that there were, of course, there were square matrices, and we could generate n linearly independent eigenvectors out of those, right, that those eigenvectors can span the n dimensional space. Okay. So, in the case of defective matrices, if I compute eigenvectors, there will be less than n linearly independent eigenvectors. So, they will not span the entire n dimensional space. And what was one of the conditions, or the necessary and sufficient condition, it was an if and only if condition, that it should have n linearly independent vectors. Okay. Now, what do I do with matrices who, say for example, have n minus 1 independent vectors? These are called defective matrices, and therefore they are not diagonalizable in the standard way. So, we need to find a way around this. Is there something that I can do here, right? So, how to get a basis is to use what are called as generalized eigenvectors. Okay, what do this mean? A generalized should be a vector of an n cross n matrix A corresponding to a certain eigenvalue lambda is a non-zero vector x satisfying this one at A minus lambda I. So, what was the traditional thing that we did was A minus lambda I n times x was equal to 0. Okay. So, so if I do it this way, I do not get n independent eigenvector. So, I just look at the higher powers of this matrix A minus lambda n, and where p is a positive integer, or equivalently this is a non-zero element. So, I am not interested in the 0 eigenvector, right. I am always interested in finding non-trivial solutions of this, and therefore, if A minus lambda I n was invertible, that was not it was not always exciting for me, right. So, I always was looking at of A minus lambda I n being a singular matrix, and it should not be invertible. Okay. So, it is a non-zero element, so this is important, of the null space of this matrix A minus lambda I times p, A minus lambda I n to the power p is equal to 0. So, the value of p corresponding to an eigenvalue can be at most the algebraic multiplicity, and let us say it is denoted by some number ki, which means that if I have an eigenvalue, say lambda 1 occurring 3 times, then this p can at most be 3. not more, it can never be greater than 3, right. We possibly will not get more eigenvectors if you do that. And well, the standard eigenvectors are of course generalized eigenvectors or a special class of it, with p being equal to 1. Okay. Now, these generalized eigenvectors, now these vectors, they will actually form a basis for the entire Rn space, in the case when matrix is defective. When it is not defective, I can just find n independent vectors and this will form the basis for Rn. What if the matrix is defective? Then I look for the generalized eigenvectors. Okay. So, how do I compute this, right? Let us start with an n by n matrix with an algebraic multiplicity of lambda, with the lambda occurring k lambda times. That is how we define the algebraic multiplicity. Okay. Now, to find the generalized eigenvector, I just define an expression which is like this. Okay. And I am again, so looking at solutions, non-zero solutions to an equation like this, right, equation 1. Okay. So, if I go about doing this way, so what I get as a first expression is a minus lambda I n times x2 is x1. Okay. And this will result in an expression which is a power minus n square x2. This I can write as a minus lambda I n, a minus lambda I n times x2. Now, what do I know about this guy? This guy is a minus lambda I n times x1, and this I know that x1 is already an eigenvector, right. So, from here, so this will be 0. So, this is how I compute the generalized eigenvectors, right. So, then similarly you can do for the cube and so on, right. So, so you can just visualize them as a chain, right. So, that what I have is a minus lambda I times x1 is 0, and similarly a power lambda I times x2, sorry, a minus lambda I times x2 will give me x1, a minus lambda I times x3 will give me x2, and so on. Okay. And this will give me say k lambda different eigenvectors. Okay. As a simple example, let me go with this matrix, right, 0 1 1 0. So, it has eigenvalue 1 and 1 with algebraic multiplicity being 2, and the only possible eigenvector is 1 0, right, if you do it in the standard way. Now, I can I find the second eigenvector, right. So, can I write can I find a solution to this a minus lambda I times x2, which is x1, right. So, now I know what is x1. Can I find what is x2 from this? And I can just solve this to find x2 as 0 and 1. Okay. So, this 0 1 is and 1 0 are generalized eigenvectors of this matrix A corresponding to this eigenvalue 1. Okay. So, before we even talk of diagonalization of what can I do when I have generalized eigenvectors, or when I cannot, or the matrix A does not have n independent eigenvectors. Okay. So, let us first define the concept of a block matrix. Well, I think from the definition it's or from the word it should be intuitively clear, but let's just write down mathematically. So, let us say I have a matrix of dimension 4 times 4. I can split it into smaller submatrices, right, this and this, this and this, or I can also do it, there are several ways of doing this, right. So, this could just be a 1 cross 1, and this could be 1 cross 3 and so on, just and that the overall dimensions should agree. So, these A, B, C, D in both these cases are referred to as certain blocks of X, and these A, B, C, D which are submatrices, they can be of any dimension as long as they are together in consistence with the block matrix. Say if I can have a 1 cross 1 here, but I possibly cannot have a 3 cross 2 here, right. So, that dimensionality should be consistent. Okay. So, the blocks along the diagonal, so this A and D in both these cases are referred to as the diagonal blocks. And a nice property of this is the following, right. So, if I have blocks of A1, B1, C1, D1, A2, B2, C2, D2, they just multiply according to the standard multiplication norms of A1 times A2 plus B1 times C2 and so on. So, this is pretty standard, and that is a pretty nice looking thing that will help us. Okay. So, a special case is a block matrix, right. So, or a block diagonal matrix, where I just have blocks in the diagonal, or so whose diagonal blocks, so here A and D were the diagonal blocks. So, these diagonal blocks are square matrices and the off diagonal ones are always 0. So, this being square is also little important here, like here these are actually they were square matrices here. Okay. So, now this once I have block diagonal matrices, it has some neat properties again. The determinant is of this matrix A would be the determinant of A1 multiplied by the determinant of A2, and so on if I have n blocks. And similarly with the trace will just add up. Sorry, there is a little typo here. So, this is trace of A1, trace of A2, so on until trace of An. Okay, this is again, these are all very easy to verify. Similarly with the inverse, right. So, A inverse would simply in this case be A1 inverse, it will again be a block diagonal matrix with A2 inverse, right. And eigenvalues, what are the eigenvalues of this block diagonal matrix A? They will just be the set of all eigenvalues comprising of eigenvalues of A1 all the way till An. Okay. So, one thing that we can answer now, which we started with, that what if I cannot find n independent eigenvectors, can I actually diagonalize? Well, you cannot, well, we can possibly not write all the diagonal elements as a set of eigenvalues, but there is some way around. There is a little trick we can still do and still get something which will look closer to a diagonal form. We can not write it in a diagonal form because we violate the necessary and sufficient condition. So, the answer to that is to write my diagonalization as a Jordan normal form, or what is also called as the Jordan canonical form or the Jordan matrix. So, a Jordan matrix is a block diagonal matrix whose diagonal blocks are all Jordan blocks. Okay, what is a Jordan block? So, let us say I have an eigenvalue. So, Jordan block associated with lambda, which is an eigenvalue, is a square, right. This is always be a square upper triangular matrix whose entries are all lambda on the diagonal, and there will be the entries 1 immediately above the diagonal. So, if I just go to the right, I just put a 1 here and a 0, right. So, everything else will be 0, and these numbers here, the lower triangular block will always be 0. Okay, so that is why we say I get an upper triangular matrix. So, in a Jordan matrix, each block can be associated with a different value of lambda. Okay, we will slowly try to understand what this means. So, just as an example, just say that I have lambda equal to 2 with an algebraic multiplicity of 3 and lambda equal to 3, right. And this if the geometric multiplicity here is 1 and the geometric multiplicity here is 1, that will result in two set of Jordan blocks. One is the one corresponding to the eigenvalue 3, and the second one would be the one corresponding to eigenvalue 2, which occurs 3 times, right. This has an algebraic multiplicity 3. This is geometric multiplicity, this is algebraic multiplicity. Okay. So, if this occurs, then say what do? I just put a 2, 2, 2 as a just like as a recipe. I can just remember this, and I just go here and just put 1, 1 and 0. Okay. So, different things combinations are possible, right. You can ask a question of what if I still have lambda equal to 2, lambda equal to 3 and say this lambda equal to 2 has a geometric multiplicity of 2, algebraic multiplicity of 1, and this can just be 1 comma 1, right. Algebraic multiplicity of 1 and geometric multiplicity as 1. So, this has an algebraic multiplicity of 3 and geometric multiplicity of 2. Okay, it is the same as here, right. So, I just increase the geometric multiplicity by 1. So, in this case I will have a Jordan block which will look like this 2, 1, 0, 2, 0, 0, 0, 0. So, this will constitute my one Jordan block, because I have 3 now in total. I have 2 independent eigenvectors from here and 1 independent from vector. So, so the second so I will have a 2 again here, and I will have finally a 3 here, right, and all the others will be 0, 0 and 0. Okay. So, I can still do it with, say, what if say I have okay, I will write it on this sheet here. If I just have again lambda equal to 2, lambda equal to 3, both have algebraic multiplicity of 2 and geometric multiplicity of 2. I can rewrite the Jordan block as, say, 2, 1, 0, 0, and corresponding to this will be 3, and corresponding to lambda 3, which has again algebraic multiplicity of okay, this should not be.
If both are same, then it's just the diagonal.
Just a diagonal, right? Okay.
It will be 2, 2, 3, 3 and rest all
Yeah,
0.
yeah. If it so in this case, so the algebraic multiplicity and the geometric multiplicity are equal. So, I will just have 2, 2, 3, 3 and the remaining all being 0, and you can do several combinations of this. So, this is diagonalizable because the algebraic multiplicity and geometric multiplicity corresponding to that eigenvalue are equal. Okay. Now, okay. So, how do we construct this Jordan form? Okay. So, the diagonal matrix is a special case of a Jordan matrix, which each diagonal element forming a Jordan block. So, if just to simply look at the example here, I can call each of this to be a Jordan block, right, corresponding to each eigenvalue. Okay. Now, the question is, can I, given a matrix A, like a square matrix, can I transform it into a Jordan form, and what is the transformation matrix that does this trick for me? So, it's the same as before. So, I can write J as P inverse AP, where the model matrix P, which transforms A to J, this will now comprise of generalized eigenvectors of A as its columns. So, okay. So, before I even go here, right. So, let us see of why this rule we learned, that anything. So there is rule at that I will just put the lambdas on the diagonal and all 1 on the entries immediately above the diagonal, right. So, where does this come from? Again, I will do a little illustration and hope that will be useful in understanding. Okay, let us say I have again for illustration, it is easier to work in R3, and I have a matrix A which has the eigenvalues lambda 1 and lambda 3, and let us assume that this has a geometric multiplicity of 1 and an algebraic multiplicity of 2, right. So, the 2 is clear. Okay. Now, what do I know, right. So So, this I can find two independent eigenvectors, let me call them x1 and x3. If I just, so this will come as solutions of A minus lambda 1 I times x1 is 0 and A minus lambda 3 I x3 equal to 0. Okay. Now, I need to find another eigenvector. So, that will come from, okay, so let me just recall this expression. Of a generalized eigenvector. So, this expression, if I rewrite this, I will get an equation which looks like this: A minus lambda 1 I times x1 is equal to x2. And if I rewrite these equations again, so in the standard form I will get A, okay, sorry, there is a little typo here. So, times x2 is x1. Okay. So, I will have A times x1 is lambda 1 x1, A times x2 is lambda 2 x2 plus x1, and A times x3 is lambda 3 x3. Okay. Now, if I rewrite this in the standard form, I can just see why these entries 1 occur here. Right? They are essentially because of these additional terms over here, which we use, which comes from here to calculate the generalized eigenvectors. It's a little illustration of not a proof, but why we follow this rule of putting this once here, and you can just write down the further details for yourself. Okay, so I have a Jordan matrix with eigenvalues. Sorry, I have a matrix A with eigenvalues 3 and 3. I just want to write down its Jordan form. So first, let me calculate the eigenvector. So x1 would be 1 and 1, right? And then I just do A minus lambda I times x2 should give me x1. So, this will give me x2 which looks like 0 and 1. Okay. And then I do can just do this. So, my P is now 1 1 0 1, and if I just compute P inverse A P, this will be 3 3 0 and 1. You can just do the computations and check for yourself. And all the other properties which we had earlier of computing higher powers of A. So, here if I write A would be P J P inverse. Okay. So, I can just say similarly A square will be P J square P inverse and so on. Similarly, with A power n would be P J power n P inverse and so on. So, those properties still would exist. Okay, let us pause here for a while, and then we will discuss what if the matrices are not square. See you in a bit.